In part 2 of section 16, we're going to introduce two new parent functions to our library of parent functions. They will both be examples of rational functions. The first one is going to be seen here in example 16.4 called the reciprocal function. It is given by the equation f of x equals 1 over x, and we are asked to do several things with this equation. First thing is to define f over the largest possible domain, and we're supposed to use a t-chart so that way we can graph f in the Cartesian coordinate plane. And finally, we're going to use limit statements to describe each behavior that is represented by an arrow on the graph of f. So more on that to come. We definitely need to complete the graph before we can go on to the limit statements. But before we do that, let's get the largest possible domain for this function. And the largest possible domain, looking at the denominator, since there's only an x down there, that means that the domain of f would have to be negative infinity to 0, union 0 to infinity. So we will define f as follows: f colon, copy down the domain. This is what maps to other real numbers, given by f of x equals 1 over x. So that's our function definition. Now we're going to make a table, and we're going to make a lengthy table here because I want to see a variety of values plugged in, such as -3, -2, -1, -1/2, -1/3. I'm going to put 0 here just as a placeholder, but I know that 0 is not supposed to be allowed because that is one of my domain restrictions. Then I'll move to the positives: 1/3, 1/2, +1, +2, and +3. So we'll start with something simple like +1. If I substitute in 1, we'll have 1 divided by 1, which is just +1. 1 divided by 2 for plugging in 2, and that's a perfectly good representation. Plug in 3, and you'll end up with 1 over 3. Same thing happens with the negative integers. If I plug in -1, 1 over -1 will be -1. 1 over -2 is typically called -1/2, and then 1 divided by -3 would be called -1/3. Now on to the fractional inputs. If I plug in 1/2, then my statement would say 1 divided by 1/2. But dividing 1/2 into 1 can also be thought of as taking 1 and multiplying it by the reciprocal of 1/2. And the reciprocal of 1/2 would just be 2, and 1 times 2 is 2. Now, if you recognize what just happened, then you understand where the name of the function comes from. This is called the reciprocal function, because what it does is it takes whatever x value you want, and then it uses the reciprocal of that value as the corresponding y value. So you can see how 2 maps to 1/2, 3 map to 1/3, 1/2 maps to 2. So then you would say 1/3 maps to 3. And -1/2 would have to map to -2, -1/3 would have to map to -3. And with 0, there is no reciprocal of 0, because then you would have a division by 0, and that would be consistent with us saying that the domain was restricted at 0. So we would just say undefined to go with 0. Again, not required, but I'm using it just as kind of a placeholder in the table between the negative inputs and the positive inputs. Now let's go ahead and plot all these points. And there's several to have to plot. And we'll notice that all of the positive x's are going to end up plotting in the first quadrant. And then all of the negative x's, when we plot them, those are all going to be in the third quadrant. Now, if the pattern were to continue in the positive x's, let's say that I go to positive 4 for an x, well, then I should end up with 1/4. If I go to 10, I would end up with 1/10. So even if I let x become really, really large, I'm always going to end up with a really small value for the y because of the reciprocal nature, the way that it makes it a fraction. So I'm never going to actually be able to get to a y value of 0 because of this. That means that there's this natural boundary along the x-axis. And this boundary is what we call an asymptote. So if I was to continue to draw the curve, I would have an arrow going off to the right, but the implication here is that the graph is going to continue to decrease, but it's just going to get closer and closer to the x-axis. It's never going to actually get to there unless we were to somehow be able to go all the way out to infinity, which is not realistic. We can't really do that. And the same kind of thing happens as we continue to finish the rest of the first quadrant. If I continue to connect the points together and I start to go up, I'm not actually going to be allowed to touch the y-axis because the y-axis represents the domain restriction. So we have here another boundary, if you will, and this one is called a vertical asymptote. So that vertical asymptote ends up running all the way up and down the y-axis there. And it has an equation. It has an equation of x equals 0, which is exactly the restriction that we came up with. This is known, again, as a vertical asymptote. I'll write that down. And the third quadrant is going to end up looking the same, and we're going to have this vertical asymptote here that's going to have a boundary effect on us, and then that horizontal asymptote is going to end up going all the way across the x-axis, even over to the left-hand side. And so we'll have a restriction there, or a boundary there, as we're going all the way to the left. So back up here in the first quadrant, I need to draw this arrow going up as it's getting closer and closer to the y-axis there. And both of these blue curves together represent the graph of f. One of the curves uses the domain negative infinity to 0. The other curve uses the part of the domain 0 to infinity. And I'll go ahead and make a note here about the horizontal asymptote. The equation for that horizontal asymptote is y equals 0, and that represents the only y value that will not end up appearing in our range. And so basically the horizontal asymptote is a range restriction. And we haven't really talked much about range as of late, but with rational functions we do have the ability to now be able to talk about the range restrictions as well, and they would be the horizontal asymptote here. Now the last part of this conversation needs to be on the limit statements. So the limit statements are specifically used to describe each one of the arrows in this graph. There are 4 different arrows which are representative of places where the function is going to be going off of the viewable window. So let me write down here limit statements, and I'm going to write down the structure for all 4 of them. Now the first 2 are going to be analogous to the end behavior that we had in the polynomials graphing section. That was I believe section 14. So we would say y approaches something, as x approaches positive infinity. Then we would also have y approaches something as x approaches negative infinity. So the x approaching infinity, I'm going to call that statement number 1. That is going to go with the arrow that's all the way here on the right. The second statement, where it says x approaches negative infinity, that's talking about the arrow going all the way over here on the left. But we still have 2 arrows. We have a third arrow that's up here close to the vertical asymptote on the right side, and then we have a 4th arrow down here to the left of the vertical asymptote. So every vertical asymptote is going to end up having an arrow on the right and the left-hand side of it. So we're going to indicate these 2 statements by using a superscript notation. I'm still going to say y approaches something as x approaches, but I'm going to say for the right-hand side of the vertical asymptote, I say x approaches 0, and I put a little superscript plus, and that plus means right-hand side. So the right-hand side of 0, because x equals 0 is the equation for that particular asymptote. And then for the 4th statement, I would say x approaches 0 from the left, and I use that with a negative as a superscript. So that negative symbol there means left-hand side. So now let's talk about what are the y values doing as we look at these different arrows. Statements 3 and 4 are going to be a lot like the in behavior that we had from polynomials for the y value. So that would be for statement number 3, you can see how the arrow is going to be going up, 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 up as we get closer to that vertical asymptote. So that would be y is approaching infinity as x approaches 0 from the right. For statement number 4, we can see the arrow is going to be going down, down, down off of the window as we get closer and closer to that vertical asymptote. So we'd say y approaches negative infinity. And then the last 2 statements are going to be for the arrows going off to the right and to the left. Now, every arrow has 2 directions. It's not just going off to the right at number 1, it's also decreasing, getting closer and closer to the x-axis. So we're interested in describing what is the y value doing as the x value gets larger and larger. So we know that going to the right is the x getting larger and larger, but the y value is getting closer and closer to 0, because that is the value of the horizontal asymptote. Same thing is true for statement number 2. As I go further and further to the left, my arrow is going to be getting closer, or my curve, I should say, is going to be getting closer and closer to the x-axis, just from the bottom, from the underside instead of the top side. But I'm still going to be approaching a y value of 0. So those are the limit statements. Rational functions are known for having vertical asymptotes and horizontal asymptotes. We still have one more parent function to go. We'll look at that in example 16.5.